We have an update from our friends across the pond. We have Mr. David Bowman, G0MRF from AMSAT UK.
Okay, thank you very much. Very good morning to everybody. Lovely to be here in Texas. I think my body clock is just about adjusted. And thank you very much for a very interesting trip out last night to a Texas steakhouse. Don't get many of those in London, I can tell you. What I'm going to talk about for the next few minutes is amateur satellite projects with a European perspective. This will be highly biased towards AMSAT UK's next mission, but we'll also take a look at the end at some interesting things that are going on with geostationary possibilities, which I'm hoping will generate some interest here in the room. So let's have a look at a little bit of recent history from AMSAT UK. In the last 10 years, we've been involved in these 6 missions. Some of these hopefully will be fairly familiar. We've got AO-73, our first CubeSat launched in 2013. Still operational in space, just coming up to its 10th anniversary in November. 1U CubeSat, designed, built, funded by the UK and our partners in Holland. And at the moment, it's done 9 years without a hiccup. Around October last year, it developed an issue with its power supply system, whereas instead of charging right up to 8.3 volts on the batteries, it's now charging for some reason up to about 7.8. So at the moment, we've taken off the transponder, and this is flying educational telemetry in sunlight. And we always put something in there to detect eclipse periods for power saving. And at the moment, it's in receive only when it flies into eclipse. If you want to save batteries, it's really that depth of discharge in eclipse that kills them. We usually run this at about 6% depth of discharge, and it's still working 10 years later. Working quickly around the screen, based on the success of AO-73, we had a payload on UCube-1, a mission from the UK Space Agency, 3U spacecraft with deployable panels. That was a 1-year mission for the Space Agency, and our transponder on that ran for about 2.5 years after end of mission. Ended up with a probable battery failure. It was one of those thin lithium polymer battery packs. And we've got one piece of telemetry that shows the battery temperature rapidly going up, and then that was the end of the satellite. So, probable cause, I guess, that something happened to the battery there. EO-79, a sort of a thank you from the von Karman Institute. We had just a transponder on that, no telemetry of any sort. It flew a couple of sensors they wanted to check, and because they were launching a lot of satellites using amateur radio frequencies, they said, okay, we'll provide you with space for a transponder, and we took advantage of that. EO-88 just re-entered, launched at 500 kilometers, so an important figure, 500 kilometers, lasted 6 years. It re-entered earlier this summer over the Pacific, just off the California coast. I've got the most amazing piece of telemetry there. Someone was recording it on SACNOGS, and if you look at that picture, you can see the temperature rapidly increasing as it came down into the atmosphere, 91 degrees before it failed on the external surfaces. So that was quite an interesting one to capture. JO-97, a mission with the Jordanians. That's still in operation, still in transponder mode in Eclipse, so that's very good. Oh, actually, it's transponder mode the whole time. And one of the 2 missions we've had at the end there with the European Space Agency Education Office, ESSEO, talk a little bit about that in a moment. So after all of that, we can have a quick look at the experience we've gained, the lessons we've learned. And as you can see there, we've got a summary of the mission duration. AO-73 still active. UCube-1 failed probably from a battery failure, 3.5 years into the mission. EO-79, the von Karman Institute 2U satellite, ended up with a negative power budget. Because of the limited amount of things we were flying on that, we had no way of correcting it. There was a great deal of effort from ISIS Space in the Netherlands to come up with some new firmware to switch it on for limited periods of time in its orbit so it could charge. But unfortunately, there was so much work doing that software updating. It had about 6 months of operation and then finally died because of the negative power budget. EO-88, very successful, not a hint of trouble for all 6 years. Real shame to see an active amateur radio satellite burn up in the atmosphere. We've got to be careful where we put these things. There are a lot of investment. We really need to get them up just a bit higher than that so that they can last the full duration of the components in the satellites. JO-97, still working. Microcontroller failure on that one, so no telemetry, transponder only. Nice thing about most of these designs is we always try to put something just above the microprocessor controller, so if there's any trouble with the control systems in the spacecraft, we've got the ability to have I think it's a CPLD from Xilinx on all of these, so that if the digital side of it goes down, we can send a command to effectively a hardware decoder, and we can switch the satellite into different modes. So a microcontroller failure doesn't mean end of mission. ESA education, oh dear, mission duration, 0.041 years. That was about 3 orbits. They make great t-shirts. So what have we gained from that? Well, if you add up some of the parts that have flown successfully and have not failed, we've got a cumulative total of 23 years on some of those parts. So we know what works really well, but it has failed, and we know a few things that we wouldn't do in the future. Which brings us to, I think, our next project. This has gone through a bit of a revision. About a year ago, I did a presentation in the UK for FunCube Next. This started out as a 3U structure with a lot of interesting payloads, and in the intervening year, we've rationalized some of that. We've decided that what we've got left will fit quite nicely into a 2U frame, and so going forward with a potential launch date around mid-2025, we've got something that we've christened FunCube Plus, so something a little bit between FunCube Next and the original missions. So let's have a look at the details. This is what we're actively working on now. 2U will give us some more DC power above the usual 1U CubeSat. We've got 3 basic amateur radio transponders scheduled at the moment. We will probably add something a little bit more adventurous. Educational outreach telemetry in our normal format on 2 meters at 1200 bits per second. We'll probably change the data format. We've been using something designed by Phil Kahn many years ago for AO40. We speeded it up. It's really very good. I heard Nick in the front row here saying his SlimSats were going to run 50 milliwatts from orbit. We can quite happily receive 30 milliwatts from orbit at 1200 bits per second. So Nick, you really shouldn't have any trouble with that power budget. Really looking forward to that project. To keep our techies interested, and that's always a challenge, as I've found out over this week, we're going to put a camera module on. Not quite sure of the angle of that, but 6 to 10 megabyte images should be available from that. We started off looking at X-band, but we really haven't made enough progress on that to see that as a potential success by the delivery date. So we've scrapped the X-band system. We've got attitude determination and control, but only course, so we can stop the thing spinning up. We can point it roughly in a direction, but this is by no means 3-axis pointing, but nevertheless it will give us some control. We want to separate the housekeeping and the processes used for the various experimental payloads on board, just to make sure there isn't a single point failure risk there. And we want to do something like fly your code. So the experimental processor on board will be able to be reprogrammed with stuff from the ground. If somebody wants to make use of all of the sensors that we've got on the spacecraft, they can come up with a piece of code that they can simulate on the ground, and then if we think it's safe enough, we'll upload that, and they can get their data back by changing data rates that things are sampled at, things like that, back down to do projects here on the Earth. Educational outreach as well. We also wanted to fly a radiation sensor. We've identified one made in Switzerland, Michael, so very, very good. We've tested that. Seems to work extremely well for beta radiation, so electrons, gamma and X-rays, and it will probably respond to high energy particles as well if they've got enough energy to punch through the exterior housing on that sensor. A little bit more about that later. Something else we're going to look at is experimental digital processing of transponder signals. So a digital mode going up, the mode is then received, decoded back to basic data, and then retransmitted down using a different mode. And we think that will offer some advantages in tracking, I'll look at this in a few minutes, but also on receiving weak signals on the ground, which is more compatible with the power budget of a CubeSat. We also want to have a look at experimental data downlinks, probably QPSK, around the 19K bits per second in 2 meters. This won't be on all the time, you'll be pleased to hear, but it's something we want to try because we think 2 meters is potentially very useful because of the low path loss and relatively low changes in the phase of the signal as it comes down. So what have we got as a basic communication system? Well, we've got 3 payloads under development at the moment, fairly well advanced. The top row there, going from right to left, we've got the typical 70SEMS receiver that we've always flown, a linear transponder, something that converts that to 2 meters, and then a power amplifier on the right-hand side, which now has 3 inputs. So the linear transponder will be 1 input into a combiner. We can then use an FM repeater type system, taking the 70SEMS in the middle row, applying an FM demodulator to that, CTCSS, and the various timers and logic, convert that up to 2 meters, and then again amplify that out through the 2 meter PA. And then the last one is something I think we all really need to think about now, especially after Frank's talk this morning, 24 centimeters. If we don't use it, we are going to lose it. The latest bit of information I heard last weekend is that the 24/7 band for amateur radio satellites is currently 1260 to 1270. In all likelihood, that will be reduced to 1260 to 1262 at best. The Russian Federation is still saying we don't want it anywhere. It needs to go, so it's not a done deal. The last thing I heard was that it's likely to be power limited from the ground, so you don't interfere with people using the navigation systems around you. They're proposing a power limit. Don't worry, it's 5 kilowatts, ERP. But they are suggesting a 15-degree minimum angle for anything on the ground pointing to space. I think we can live with that. If you want to get down to the horizon, just reduce the length of the antenna, the beam width broadens out, you can still do it. But we really do need to use that band. So that will be FM as well, FM going in, CTCSS, timers, going into a 2 meter modulator, and then out through that PA again. Couple of little things, the high-speed data will need to go into an IQ modulator for that band, that'll be separate. And our usual telemetry will go into the 2 meter section at 1200 bits per second. So what have we got in, if you like, historical board designs? Well, the left-hand side there is the little transponder stack from AO73, UCube, Naif-1, and JY1-SAT. 3 boards stacked together, a transponder board, a CCT board, which controls it and provides the telemetry, and then another board of sensors on the bottom reading all sorts of current, and I think there might be the odd magnet, which won't be fitted to the next satellite, to keep it all pointing in the right direction. The one below on the left was some work done by a student that we sponsored down at Surrey University, our good friend Dr. Chris Bridges. We see a little less of him these days. He's become a father, and so he's got extended paternity leave. And I think amateur radio has just gone down a slight notch, but Chris, we hope to see you back fairly soon. Some great work on the 10 gigahertz project by one of the students. That was carried on this year as a degree project. We're not convinced it's gone far enough to actually take that into space, but at least it's a nice bit of research. Something else going on at Surrey at the moment, we've got a student who's just completed a project using supercapacitors as an EPS on a spacecraft. And the advantage there is supercapacitors have a much longer lifetime. You probably can't run them right the way through an orbital eclipse, running full functionality, but you can certainly keep the satellite going in terms of computer, sensors running and things like that. So very good potential there for future long life satellites. And after all, why throw things away when you've paid so much to get them in space? Top right-hand side, we've already done 1263, I think it was, megahertz for the SAO program. Survived all of the vibration testing, thermal testing that we had to do with it. That was okay. It was in space for about 3 months before it switched on, ran for about 3 orbits. So we never really got some long mission information from that, but at least it's been into space and survived the testing. Equally, bottom right-hand side, 2-meter BPSK transmitter and the 2-meter FM transmitter on SAO. Again, some more valuable experience gained. We would have liked it to work a bit longer in space, but there were simply too many failures in various other parts of the satellite to enable us to do that. So this is one of the new things we want to put on. We're sacrificing a couple of solar cells. If you can imagine a 2U satellite, normally it would have 4 solar cells down each side and 2 on each end. So I think that's 20. We are going to remove 2 of those from the -Z end, as I should say here in Texas. And instead of solar cells on that panel, we will be putting an aperture in for this radiation sensor, the lens for a camera, and also, because we've got 24 centimeter band, and we don't want to run a patch, because a patch antenna is likely to take up too much real estate, we've identified how to put on an antenna which is actually not a deployable, but it's fixed. Thanks to Planet Labs, who've been using 3U satellites in low Earth orbit for a long time now, they identified on a CubeSat deployer, you have a spring at one end, ready to push out the satellites below, and on the inside of that spring, you've got a little area that's totally free. So there's a little void there that nobody uses. And it's possible to put things on the outside of the satellite, so to normally exceed the envelope of the CubeSat and put something into that space. Some people call that the tuna can extension because that's about the size of it, but it is possible to put some deployables there. We wondered if we could put in a 23 SEMS quarter wave. It doesn't quite fit, so we had to think of it being moved slightly to one side to reduce the height. We like fun, so we came up with a little design challenge here and came up with the scary antenna, the slightly canted antenna resistant to impacts, because if you imagine that CubeSat going up and down, there's a fair chance that antenna tip is going to hit the end of the deployer. So we needed to make sure it was at an angle so it didn't transfer the energy straight into the mounting. So if it does go up and down, it's got to hit the end of the CubeSat deployer and just bend very slightly, so we need to protect the top of it. But we reckon that will give us a better radiation pattern than a patch on that particular end of the satellite. So that was quite good fun. Okay, last thing on this FunCube Plus mission, Mode Dynamic Transponder. Not the best name, we'll probably change that. But it was one of those conversations that came about at a late night conversation, much the same that we are having here this weekend. One mode up in digital format and another down in a completely different format. We've heard this morning, let's use a couple of examples. IO117, packet radio, 1200 bits per second up, loads of people transmitting all at the same time, only one user can get in, and we have people in Europe who sit there with their finger on the transmit button going CQ, 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 until they get into the satellite. Only one channel. It's a real challenge because even I get a 10-minute window with Hawaii on that satellite every few days. The coverage is immense. The reason for this idea is that uplink power for us is not restricted. We can turn up the power, we can add more elements to the antenna, and we can transmit faster with a wider bandwidth without too much trouble. You can't do that on the CubeSat. Downlink power there is limited. It needs to be a relatively high efficiency mode, preferably with forward error correction. So just as a wild and wacky idea, we're not sure of the modes yet, but just imagine you transmit up to a satellite using, let's say, a packet format, 1200 bits per second. The transmission is about 1 second, maybe a fraction longer. That can be received by the satellite, decoded back into its basic data, and then transformed into another mode which is more appropriate for sending down. I've no idea what that might be, but I've seen people using FT4. Okay, so imagine that idea. Good thing about this is you can also define the bandwidth of the transponder depending on the band you're using. We all have to track satellites to get things in the right place. You may not have to do that with this. If you say you're going to transmit up, let's say on 70 centimeters, you know what the Doppler shift is going to be. It's about 10K one side, about 10K the other. If you make the transponder 25 kilohertz wide, if you transmit in the middle of that uplink band, no matter where the satellite is relative to your position, your signal will always be in the transponder passband. So you don't need to change the frequency. What will happen then is you can get more than one signal into the satellite at the same time because you've got a big chunk of bandwidth. The satellite can handle each of those signals, decode them back into data, and then produce some nice parallel narrowband streams on the downlink, which you can receive in a much smaller bandwidth. It's good for the satellite, it's easy for us, no tracking. It's something that was a wild and wacky idea, but we think it's got potential. Next stage on that is prototype with GNU Radio, and then if it all works, transfer it to an FPGA and fly it. Okay, we've heard about QO100. That thing has a pesky little end of footprint right down the middle of the Atlantic. Two things that have been going on in Europe. Firstly, a company called Space Inventor in Denmark launched a 16U, I hesitate to say CubeSat, that's big, isn't it, for a CubeSat, but a 16U satellite into an orbit 1,000 kilometers under the geostationary belt, using some interesting propulsion technology, new products that they're developing, star trackers and things like that, and this satellite is covered with horn antennas for the microwave bands on one side of it for its main mission. They gradually nudged that up from 1,000 kilometers under the geostationary belt right into the slot that they've been allocated for this satellite. So a lot of interesting technology there, and in the future, they may be interested in hosted payloads. So just keep half an eye out on developments from Carl and his team at Space Inventor. Last but not least, European Space Agency. They've recently started to seek proposals for an amateur satellite or payload to geostationary orbit. I think they've seen some of the developments that have gone on with QO100. Lots of people coming up with new modes, lots of people doing research work on amateur television, and the progress has been really quite amazing over the last few years. So a few weeks ago, Frank Zappenfeld, Papa Delta Zero Alpha Papa, who works for the European Space Agency Telecommunications Division, came along and told us of an interesting discussion that he had been having with his colleagues and the people who run ESA funding. They're looking for proposals for either a hosted payload or a microsat to geostationary orbit. The important thing is that it must serve the radio amateurs, and this is amateur radio based, that are in countries that form the European Space Agency or their cooperating states. And I can't help noticing that one of the cooperating states is just north of here, the whole of Canada. Now, I don't see how you can run a geostationary satellite serving the amateurs of Canada without it coming into the USA. And AMSAT North America has members in Canada. So guys, get thinking about it. If you come up with an idea, they're interested in things like 5 gigahertz, 10 gigahertz, 24, maybe 77. Come up with some ideas, get some proposals in. They're willing to put money into it. 250,000 euros has been already funded for the feasibility study, and if that's successful, it'll go forward. They're looking for 2 proposals, so they've got something to discuss, but that is it's an opportunity that's gone further than most that I've seen, so it's likely to be ongoing, which is really good. Okay, that's it from Europe. Thank you very much.
Thank you very much, David and Michael. At this time, I would like to take a little extra time out of your lunch, if you don't mind, to give you an opportunity to ask either one of these gentlemen a few questions. So, Michael, if you'd go back up and we can get a few questions from the audience. I think Kent has a first comment.
Good day. Been a while since I've met you at Martlesham. I do find your use of the 4-meter band interesting. I'm probably one of the few people on this side of the pond with a 4-meter station. But here it is classified as white space. So we can, very similar to the various ISM bands, use it on this side of the pond with a few restrictions. So there's no reason why more people can't get on it.
Okay, yeah, I think that's good. Obviously, the higher bands that we can use, the better. Sorry, I don't feel a patch from your good self is the most appropriate antenna for our new satellite, but we're aware of your work, and I'm looking forward to the presentation this afternoon. Okay, there it is. Any more questions?
Yeah, thanks for the presentation. It's very interesting. I'll just say that I like the idea of the mixed mode transponder from an experimentation perspective, and close to the microphone. And certainly, one thing, these complicated modes with lots of efficiency and forward error correction are much easier to generate than they are to decode. So, you're better off transmitting it from the satellite, but not having to receive it, perhaps. So you could get some real efficiency out of that. So look forward to that.
Yeah, okay, thank you. I sort of anticipated the decoding would be a challenge, and I can see that, we've gone for the forward error correction and the more difficult modulation schemes in the downlink, anticipating that what needs to be generated on the ground must be perhaps easier, because it's a lot of people doing it, so it's got to be easy. Okay, thank you, Chris.
Any other questions? Okay.
If you would like to see one of our CubeSat boards for this new mission, this has just come in, and I'll leave it at the front. It's a 2-meter PA with a combiner and all sorts of telemetry and an FM transmitter on the back of it. So that should be flying in mid-25. Thanks.
Excellent. I would like to extend our appreciation for the 2 of you doing your presentations today. These gentlemen did not know they were going to present today. So all of this was off the cuff. They did an excellent job. Thank you very much for the update.